Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And in this video we'll be talking about how you can get better insights in your geothermal simulation when you use hourly data. Now, we already talked quite a lot about hourly data on this channel, but we never really talked about the advantages when compared to monthly data. So hourly data is when you have measurement data for your building, but most often you have a simulation of your building. Based on a weather profile, you put the 3D model of your building into a simulation software like ISV or Design Builder or Fabi Elements or IDIs. And this simulation software gives you back an hourly profile for both heating and cooling. And sometimes also dehumidification, etc. And with this hourly profile, you can do quite a lot of things in GHEtool, and we already talked about active and passive cooling. We talked about hybrid systems, optimization and simulation as well. And it has quite some advantages, but also for just interpreting and getting insights from your design, from your temperature profile, it has some advantages to use hourly over monthly data. And that's exactly what we will be covering today. So sit back, relax, and we are jumping into GHEtool right away. So here we are in GHEtool Cloud, and I created a new project with 4 scenarios for you. So we will be talking about 2 different case studies, one for a residential building and one for an auditorium building. Both are real buildings for which we have this hourly data available. And what I did is I took the hourly data and I calculated what the yearly peak heating, peak cooling demand was, as well as the yearly energy and cooling demand. So with this yearly values, I simulated my profile, or I sized the bore field based on a monthly resolution, like you typically do in feasibility studies, etc. And then what we're going to be doing is taking a look at, okay, what if we now did this simulation with an hourly resolution, with the highest resolution possible. So that's exactly what we will be doing and discussing the differences in results. So first, the residential building. The input parameters are not that important, but I want to stress that for the bore field, we have a bore field of 150 meters deep, 4x7. It's a multi-family residential building, a couple of apartments, somewhat short of 5,000 square meters. For thermal demand, the domestic hot water consumption was estimated to be 60 megawatt hours per year. And the peak heating, 62, slightly higher peak cooling of 77 kilowatts. But as you can see, the yearly heating demand with 120 megawatt hours per year is way higher than the cooling demand. So typical residential building, let's say in Western Europe. Now if you take a look at the results, this is a profile we end up with. And what you can see here, it's rather well designed given our temperature boundaries we typically use on this channel of 17 degrees and 2 degrees. Now what you would see here is that this bore field is more critical, let's say, in cooling, because we're really close to the 17 degrees. We are at 16.8, whereas the minimum temperature, there is slightly more bleeding room. It's 2.6 degrees there. So when we have this monthly data simulation done, I would say, well, this bore field is sized correctly with the information I have. Now, the interesting thing is when we take a look at the hourly profile. So what I now did is I imported the hourly load profile directly from my simulation software. I have the same 60 megawatt hours per year. And these are now the results. So as you can see, we're way closer to the minimum temperature limit. So before we were at 2.6, which was a very good margin from a minimum limit. Now it's 2.09. So it's still good, but it's way closer, and it's something we would not have expected just based on the monthly load profile. On the other hand, when we take a look at the maximum temperature profile, well, here it's at 16.37 degrees, but if we would zoom in, you'd see that it's only 1 hour that it reaches it. So we're way farther away from our maximum limit than we are from our minimum limit. Because if we would zoom in on that one, the minimum temperature, so what is it? It's December, February in the final year. You'd see that we're really a whole week very close to this minimum limit. So there are some differences, and notice that the imbalance and etc. is the same. So what explains these differences? Well, first of all, we have with the monthly profile an estimation we have to make for the peak duration. And this is, we already discussed that, but the peak duration is basically when the heat pump jumps on, how long does it run at maximum power? And this has to do with your emission system, whether it's a slow emission system, concrete core activation, floor heating, etc. Or it's a fast emission system, air-based, with the air handling unit. But it's a really hard parameter to estimate. And if you use an hourly resolution, you don't have to estimate that because it's embedded in the hourly resolution itself. So if we compare it and we say, well, this is a good design, this is actually also a good design, but it's a good design for another reason. And that's the first message I want to give. If you have hourly data, you have way better insights in how your profile should be sized. You know more what you're doing. And that's not because hourly profiles are by definition true, because it's also based on a simulation model, which can also be fed with wrong assumptions, wrong occupancy, behavior, etc. But the thing is that you know how the profile behaves and how the building behaves based on weather data. And that's an interesting extra nuance that's embedded in hourly data, and which you can see in this case. Now, for the other simulation, let's jump to the bore field tab. We have an auditorium with 9 by 4 boreholes. In our thermal simulation tab, we have no domestic hot water. We again use the default values for 8 and 8 here. And we see here that we have a maximum peak power of 32 kilowatts, but way more cooling power. And that's also typically something you see with auditoria or theaters, movie centers, etc., where there are quite a lot of people at one place. There's quite a lot of cooling demand. But on the yearly energy level in our climate, it's typically more heating than cooling, almost a factor 10 here. So if you would design this bore field, you end up with this temperature profile, nothing too spectacular here, clearly limited by the cooling demand. An office building would look something familiar here. Now if we go to the hourly profile, we see this result. And here we see that we are at 16.16 degrees Celsius. And yeah, the minimum temperature is even nowhere near, but the difference between this 16.85, which is a good design, I would say, and we're just below this limit. Here we're just oversizing based on this hourly level. So if I go ahead and say, well, let's remove 4 boreholes and make it a 4x8 bore field, you'd see that we still have too much boreholes. So we can even go further and go to 7x4, for example. I'm just trying to play around a little bit to end up with a bore field which is actually better sized. Okay, now it's slightly above, but if we would zoom in and see, well, is it really a problem? And you can see it's just 1 hour. It's the 10th of August at 3 a.m. There is a problem. But the rest of the year, we're still below this threshold. So in this case, I would say that we're now at 28 boreholes. It's still on the safer side because you can clearly see here this cooling peak, it only occurs once. You have here, when is it? It's in May, also a higher cooling peak. But these 28 boreholes are actually more than enough. And if you would use a monthly profile, we would end up with 36 boreholes, because you say, okay, in this month, yeah, we reached this 16.85 degrees Celsius, but you don't know when or how long, because you're working on a monthly scale and you don't have this finer resolution to really see how your system behaves at a final level. So this is basically what I wanted to show you. It's not that hourly resolutions are true by definition, but they give you a way better sense of how your system behaves. And it can show you things you would not have expected. So for example, in a residential building, but the insights can differ based on your profile in your particular project. But we saw a situation where we have a good design, and with a higher resolution, we also have good design, but for other reasons. Here for the auditorium, we are way oversized because we miss this finer resolution. So it can be interesting if you're designing bigger bore fields to also try to spend some time to really grasp how your building is behaving, because that in the end determines how your geothermal system also reacts, and you can get quite some insights from that. So this was a short video today. I hope you found it interesting. I hope you learned something about why hourly profiles are important. In the article, which is linked below, we will go in more detail about a couple of intricacies. But for now, I hope you subscribe. I hope you can share it with your colleagues. I hope you learned something new, and I'm looking forward to seeing you in the next video. Take care. Bye.